Welcome back, my geometric minions. Okay, so we've got this short video tonight looking at the area of regular polygons. So I'm warning you already, you've seen me draw, so ignore the drawings. I apologize for them, and we'll turn around and go from here. So first of all, polygons. We know we've been talking about polygons, and we said a polygon is simply any closed-sided, many-sided figure. So this is going to work for any regular ones. Remember, regular. Regular means that all the sides, all the angles are the same. Now, easy ones for regular polygons are regular triangles. Equilateral ones, equiangular. Those aren't the ones we're going to use this formula for. A regular quadrilateral is a square. We're not going to use this for a square. We've got easier formulas for that. But really, this one comes into play for those pentagons, hexagons, heptagons, octagons, nonagons, all those strange, crazy ones that come out. So here's the formula for it. And the formula is area of this is 1/2 the perimeter times the apothem. So big P, this means perimeter. Perimeter, simply the distance around the object, the distance around the outside. It's what we get from we add up all the sides. 1/2 is easy. Apothem. This is an apothem, not a possum. This is not that short, fat little animal that runs around and scurries around in front of your parents' cars at night and likes to play dead and hangs upside down if you're watching the Goofy movie and turn around in there. This is an apothem. So what an apothem is if we're looking at any polygon, and let's just take this pentagon right here, okay? We know that from a pentagon, if we were to look at the center of this thing, we could draw a circle. We could draw a circle that goes all the way around this figure. Please excuse that. There we go. So that all the vertices were on it. We could draw a circle. In other words, we could circumscribe this. And if we do, we could turn around and we could draw a segment to each of these, and these would all be radii of the circle. Okay? These would all be radii of the circle. So if we were to turn around and we were to draw 5 radii on a circle, they were all evenly spaced apart. This is how we create a pentagon. And we could use 6 of them and create a hexagon, 7 to create a heptagon, all of those. Well, if we look at, and when we do that, we've got right in here, if you look, 1, 2, 3, 4, 5 equilateral triangles. Because all of these radii are all exactly the same. The distances across the bottom are all the same. So what we've got here is we've created 5 identical triangles, 5 congruent triangles. Well, and when we want to know, we want to look at these triangles and find the area of the triangle, well, we know it's the base, the length of the base, times the height of that triangle. Well, the height of the triangle, that's what an apothem is. That's the reason for this formula. It says find the perimeter. Well, the perimeter is simply all of the bases for all of these triangles times the apothem. Well, the apothem is just the height of each one of these triangles. And we found the apothem plenty of times when we were looking at circles, because if you remember, we would look at these and what we would simply say is, hey, this is where a chord and a radius intersect. You would find these segments here, but we just didn't call them apothems. So that's what an apothem is. It's the height of each one of these triangles that we have when we circumscribe a figure. Okay, so this is different terminology, but we'll look at it from here. So here we go. We've got this pentagon. Here again, I apologize for the drawing not being perfectly regular, but we're going to operate under that idea. So I tell you right now the apothem is 5.1. So the apothem is 5.1. So we've got 5.1 units. We need the perimeter. Well, we can't find the perimeter. There's nothing that labels it. But we can find it. And go back to the same idea I said before. If we were to take, we know that the apothem is the distance from the center to one of these triangles. If we were to go ahead and draw the point here, what we are doing in effect is we're allowing us to circumscribe this. Can we find the measure of each of these angles inside of this triangle? And the answer is yes, absolutely. Because we've taken this circle and we've made it into 5 identical triangles. So How many degrees are there in a circle? 360. So what's 360 divided by 5? Well, 360 divided by 5, we turn around and take this, quick math work here, 72 degrees. So that means that each of these central angles, the central angle is 72 degrees. So if we want to know, we want to find over here, let's look at this side section of it. Let's look at the side view. Well, if the whole thing is 72, that means that this angle right here is 36 degrees. And we know that this height is 5.1. We need to know x. How do we do it? Yes, your trig functions. So looking at this, going back from the blast from the past, here's the angle. This side is opposite. This side is the adjacent. So what trig function are we dealing with? Tangent. Tangent of 36 degrees is equal to x over 51. So we need to solve for this one. So in your calculator, we're going to check our mode, make sure we are in degree mode, and we are going to solve this. We're going to multiply both sides by 51. So we're going to find that x is equal to the tangent of 36 times 51. And what that tells us is that x is 37.054. So we're going to go with 37.05. So 37.05. So that would mean, what's the distance all the way across here? That's times 2. So 74.10 is one of these legs. How many of them are there? There's 5. So times 5. Here we go. So we're taking 74.10 times 5, and we find the perimeter is 370.5 units. All right, all of that done. Now we can actually use the formula. Remember, it's 1/2 the perimeter, 370.5, times the apothem, which is 5.1. Plugging it all in the calculator, and we have the area for this one. All right, that was a learning experience. Let's take a look at another one. All right, so look at the sides. 1, 2, 3, 4, 5, 6 sides. So go ahead and hit pause on the video, see if you can figure this one out for yourself, and then come back to me and we'll see what you can do. Okay, well, welcome back. Hopefully you figured this out now and you've gone ahead and said, hey, okay, 6 sides of this thing, so 6 central angles. Take 360 divided by 6. You found that each central angle was 60. So this triangle that we're dealing with, the right triangle that we're focusing on, this is 30 degrees. So here's our apothem. It's 5 square root of 3. Hey, this is a 30, 60, 90. We really don't even have to use our trig functions if you studied well the first semester and remember your special right triangles. But if not, you're going to set up and do tangent of 30 degrees is equal to x over 5 root 3. Multiply both sides by 5 root 3. And we'll turn around and x is going to equal whatever happens when we get 5 root 3 times the tangent of 30 degrees. Or if you can really remember from back from the first semester and you remember special right triangles and remember that the ratio of a 30, 60, 90 is always x. 2x is the hypotenuse and the 60 is x root 3. You're going to find that this is 5. So x is 5, short and sweet. So if this is 5, this is 5, each leg here has to be 10. So the perimeter is going to be 10 times 6. So the perimeter is 60. The apothem is 5 root 3. So plug it into our formula. 1/2 the perimeter 60 times the apothem. 5 root 3. Get your answer in the calculator. All right, so there's a quick run through of this one. Take a look at it. I would suggest go back, watch it again. Bring questions to class tomorrow. You should have lots of them. Make sure you write them down. All right, we'll talk to you later.